QSAR, from its acronym in English, Quantitative Structural Activity Relations, because what we are going to look for is to create an equation that correlates biological activity versus physical-chemical properties. Well, let's go there first. Let's do a little historical tour on the QSAR methodology. But where does this idea come from? Who came up with it? In the year 1868, some researchers, such as Cranbrough and Fraser, studied alkaloids in rentals, and these alkaloids had biological effects. And it was said that their biological effect, represented by this Greek letter, is a function of their concentration, so there was already an idea that at greater concentration, biological effect. But this idea of making mathematical correlations, this man Comte, who was a philosopher, said that any attempt to use mathematical methods in the study of chemical reactions must be considered deeply irrational and contrary to the spirit of chemistry. If mathematical analysis in chemistry, an operation that is happily almost impossible, would put degeneration of that science. Strange, the thought. So if they could not occupy Python or anything that would help them to make correlations. Mathematics between chemistry and descriptors, 1893. Then notice how this was born at the beginning of the 1900s. That's the idea, this background idea. Richard, another reason, when the concentration varies, we could say that it is a function of the variation in the concentration used by the substance. He's already introducing the concept of variation. The concept derived, in other words. And the first, let's say, proto-QSAR is attributed to it, lipophilia versus activity. He found that at greater lipophilia, greater biological activity of what? Here we have a series of molecules: ethanol, ether, urethane, paraaldehyde, amylic alcohol, acetophenone, and even an alcoholic extract called absinthe. And of course what they did was determine that at greater lipophilia, greater depressive activity of the central nervous system, that was basically the focus, greater ease of greater depression of the neurotransmission. 1893, in the early 1900s. Just around that time, just then, Emil Fischer was stumbling upon the concept of receptor. That is, what is the key closing model for the interaction by linking proteins was being formed. Part of that, we have done it, and we are also going to have workshops of this, linking proteins. That is, a molecule fitting in a receptor. The point is that that is not thought at that time. Today, we know that the system is flexible. Both the protein, the ligand, have flexibility in their modes of union. Well, since Comte opposed this, and this came from Paris, France, this philosophical idea, you know that Paris, France, is a niche of philosophies that seek to impregnate the whole world and many times nefarious. And here, we have 70 years in which absolutely nothing happened, because it is irrational to mix chemistry with mathematics. Until here, in 1962, a North American dared Corbin Hunch, to whom he's attributed to be the father of the QSAR, of the equations of structure-activity relationship, and published nothing more and less than the Nature journal, his proposal called correlation of biological activity of phenoxyacetic acids with constants of substitutes of Hammett and partition coefficients. Let's see what I'm going to do. We're not going to see the articles in detail, but yes, extract from some of these articles the proposal of him, that is, to demonstrate whether QSAR, a little internal tour of how he comes to a proposal of a mathematical equation. Here in this photo, in the background, you can see that there are numerical expressions. Here it is saying the following. Notice, it says correlation of biological activity. Okay, then the question that is going to arise here is, does this only serve for biological activities? No. Today the concept has expanded. Today it is already talked about QSAR, which means quantitative relationship, structure property. Then here we talk about relationship structure property. We no longer only talk about structure activity, but structure property. You will say, what property? QSAR has been done, for example, in chemistry, that allows to explain of chemical reactions. What does the performance of a reaction depend? The reaction performance explained with a QSAR equation. This has expanded not only biological activity, but also, for example, toxicological activity, if we want to be more detailed in the term. This is not always going to be a biological activity in terms of biological activity. And who correlated it with? It says with Hamiltonian substitutes. What is that? Does something sound to you, Hamid? To the most chemical, I think so, right? Hamiltonian substitutes. The Hamiltonian constant, I'm going to explain it to you, is a constant that tells us the electronic nature of a substitute. It is an electron. And we are going to represent it by the Greek letter . And then, that's why the titles have to be short and give information about what is the work that is being proposed. And also, apart from Hamid's constants, he correlated it with partition coefficients. And yes, what are the partition coefficients? Perfect. Very good. The lipophilia. The Hamid contribution was to take this to a simpler way, and he spoke of the pi lipophilia. It has nothing to do with pi stacking interactions. It has nothing to do with the mathematical pi 3, 4, and 4, but it is the lipophilia coefficient of a fragment. And we are going to explain it later, because I know it sounds very strange. We are later with more space, okay? Well, when that happened in 1962, and obviously, immediately, when they saw that in the pharmaceutical industry, they said, this is scream and scream, because with an equation, we can predict things. The advantage of an equation is that you can predict, and if one can predict, it can save many later, with the help of Fujita, who was a well-known Japanese researcher who was having a sabbatical year in the United States. They too, Hansch and Fujita, published the proposal a bit and published it in a JAX. Again, this in a slightly more refined proposal, and it says analysis rho sigma p. So here we have that this sigma, the coefficient of Hamid, P, the coefficient of the Hansch lipophilia, a method for the correlation of biological activity and chemical structure. So we have that in 1964, the same proposal, a little more refined, and at the same time the Free and Wilson researchers published something super interesting in Journal of Medicinal Chemistry entitled A Mathematical Contribution to Studies, Struktur, Activity. Today, the studies of these two gentlemen are called, in fact, the studies of Free Wilson. Well, what is the subtle difference? When we talk about Hansch correlations, we talk about that biological activity, which is almost always the variable that one wants correlated with physical chemical properties. Physical chemical properties. As for example, a physical chemical property can be lipophilia. A physical chemical property can be molecular. What? Even the molar refractivity, etc. Many things can be physical chemical property. But Free Wilson has the merit that they carried out this even simpler plan by saying that biological activity can be correlated directly with the chemical structure. In other words, you can correlate biological activity with fragments of the chemical structure. You don't need to calculate anything. You don't need lipophilia or HAMD. Just see what the fragments of the structure are, and with that, you can create a mathematical equation, as you see. Now, these two gentlemen, Free Wilson, became famous because they went unnoticed by the work of Bruvius and collaborators that had been published 8 years before, but that no one had read it, and where they were practically publishing the same thing. Now the question arises whether Free Wilson perhaps read that work and made a reformulation in their proposal, which was published in a journal of better impact. So there are things that are never going to be known, and sometimes that happens. Scientifically, a correlation of tyrosine activity, that is, activity similar to thyroid hormones and the chemical structure, that is, he was already publishing a model similar to what Free Wilson posited, an additive model of our structure-activity relationships. When we say additive model, it is because biological activity will be able to be expressed as a sum of things. We can have additive linear equations. Well, then there is the base, there is the foundation. In 1968, there were researchers who all talked about the Hammett constant. We can separate it in its resonance contributions and its F-inductive effect contribution, and that both values can be used in QSAR equations, in Hansch equations. It is also called Hansch equations. 1988 was the last big leap towards modernity, because Kramer and collaborators published what was first known as a 3 QSAR study, or three-dimensional QSAR, where you are no longer going to correlate it only biological activity with flat physicochemical properties, but with global properties of the entire molecule. It says comparative analysis of molecular fields, CONFA studies, effect of the form in the union to the protein transporter of steroids. That is, they studied as three-dimensional properties. The potentials are correlated with biological activity. The activity we are going to correlate with potentials. Which potential? The two most important, the molecular electrostatic potential and the hysterical potential. The molecular electrostatic potential can be described by the Coulomb law, while the hysterical potential can be described by the Leonard-Jones equation. So it is no longer a flat property, but it is a property that can be obtained by tau, determining the three-dimensional property of the complete molecule. In summary, Hansch, as the father of the modern QSAR, established the basis of the extra-thermodynamic analysis of structure-activity relations. We are going to have many molecules with many properties. We are going to be able to graph it and obtain some kind of equation for this set of data that we usually divide into two, a set of data to create the model and another set of data to put the model to the test. So in general, you are going to divide the data into two parts. You are going to create what is called a training set. A training set which is the one that gives origin to the equation itself. With that, you have the equation y equal to x plus b. And on the other hand, you will have another set of data called the tests, which is that set that allows you to validate the equation. In other words, those test set data are left out of the model. You leave them out to validate the equation that you are proposing with them. In what proportion? More used proportions are of the type 70-30 and also 80-20. That is, 70 or 80% training set, most of the molecules to build the model, and a lower percentage to validate the model. This is very common in hunch correlations. But, and then you will understand why, in free Wilson correlations, one occupies 100% of the molecules as a training set. It is rare to have a test set because we mutilate from the structural point of view. And what is sought is to correlate structure with biological activity, and rarely two molecules are close in structure. In fact, it is impossible for two molecules of the model to have the same. So if you discard a structure, it is delivering less information to the model. In physical and chemical properties, there are always many molecules with similar physical and so on. These things are the methodology of how to proceed is very important that you have it clear. And do not forget it. As a result of all this, a different molecule arrives. Yes, there you can create several infinites. So yes, as a result of this, we are going to have an equation. And that equation that you are going to obtain basically allows two things. It allows the retrospective SAR, that is, the structure-activity relationship of the study set. That would be the retrospective SAR. You will be able to explain why that set of molecules has anti-tumor activity, antibacterial activity, antihistaminic activity, whatever. And on the other hand, you will be able to predict biological activity. That is, the prediction. That is why the QSAR is so important, because if one predicts, it is not going blind. Well, then it says what the contributions are here. It says combination, hunch contributions of all his philosophy of the study of QSAR, says the combination of parameters, or of several physical-chemical parameters, in one equation of regression. The equations of the time of hunch, so to speak, were generally electronic properties, hysterical properties, and also some different physical-chemical properties, such as fragments-type properties. He will tell you, but fragments were not free, Wilson. Yes, but they can be mixed. One can have the mixture in the same equation of both concepts. They are not exclusive. Second great contribution of hunch. He defined the parameter of the pi lipophilia. What was pi? The lipophilia of a fragment. I will explain it. And third, the formulation of the parabolic model for lipophilia activity relationships. Not that of lipophilia activity. How is that? What happens is that the lipophilia, if the biological activity is increasing with the lipophilia, it turns out that not because we have more lipophilia, there will necessarily be more activity to infinity. That is why parabolic relationship, that is, what Hunch discovered, is that there is a limit, as the lipophilia intend to increase the biological activity of a compound that, for example, needs to reach lipophilic places. After a certain point, there's a retrocess. Now in this equation, it would not be so difficult to calculate the optimal lipophilia. We would have to calculate up here mathematically what one calculates if you want to obtain this value. Very well, we would have to obtain there the derivative of that curve to have that maximum value. That is, the value where the derivative goes to 0. Ask why the activity goes down. Remember, we also explain it. If the lipo continues to increase here, some things happen. There is more than one explanation. Something too lipophilic begins to go down. Very well. An explanation is membrane retention. There are also serious solubility problems. Solubility goes down too much, and therefore, molecular mobility is blurred. Then, the big question that is sought, recapitulating in A. Gas study from a molecule library. That is, we have many molecules, a large series. How many molecules? The greater the number of molecules, the better. Theoretically, to build A lean, you need to have a different R. One needs at least 3 points. But with 3 points, we will not be able to make an equation. We need many molecules. A small QSAR could have 10, but ideally 30 molecules, and from there upwards to have a good model statistic. To a greater number of molecules, we have greater structural variability. 2 things. Why are molecules needed? Because we need to have greater structural variability. Structural variability can be mathematically defined by something called the Tanimoto index. The Tanimoto index can fluctuate from 0 to 1, and we are going to calculate it later, already for the set of molecules that we studied. The Tanimoto index fluctuates from 0 to 1, where 1. If 2 molecules have a Tanimoto index of 1, it means that they are the same, and against closer to 0, it means that the molecules are more different, structurally speaking. And second, why do we need more molecules? Because we increase the variability in biological activity. Here I am, going to introduce another numerical concept. How much variability of biological activity do we need? Is there a limit? Of course, yes. And in fact, I am going to share with you an article called How Not to Do QSAR. And there is criticized, for example, the fact that many models are reported in literature have little variability in biological value. Biological activity almost always, when one measures it, what it gets biologically is a value of IC50. Remember that IC50, and it turns out that the value of IC50, if we express it logarithmically, would go to be called PI50. And at some point we calculated that we are going to return to this. But here to answer the question, that is the least logarithm. We need a variability of IC50 of 2 logarithmic units. That is, if, for example, I have here the IC50. If I have a graph here, and I have that the maximum IC50, for example, the least logarithm of IC50 or PI50, if the maximum value is 9, for example, the minimum value, minimum, right? I would have to have 2 units, that is, and in between all the dispersion of values, that is, we need at least 2 logarithmic units. Higher range better, lower range decreases the probability of finding a model with a good descriptive statistic. If we have a narrow model, the probability of finding a good regression decreases considerably. So you need 2 logarithmic units to get a good cursor. We then have that it is going to graph biological activity versus physical properties, chemicals, or structural properties or fragments, and our efforts are going to be focused on this, on how these 2 things are going to be mixed to obtain a regression of the type I equal the sum of X sub I plus B, where the X sub I are the different physical-chemical properties, and we are going to have different coefficients. If the coefficients are positive, they contribute to the activity. If the coefficients are negative, that physical-chemical property rests on the biological activity. That is, it makes it smaller. Activities. Do not forget the biological activity, Y, is always expressed in logarithmic scale. That is the Hancher hypothesis, and that has worked well so far. That is almost always the P in IC50. So, the biological activity is usually the P and C50, and the X sub I, the molecular weight, the refractivity, the electronic coefficient of Hammett, orbital energies, etc., because we can also use quantum descriptors as well. And with an equation, time is saved, resources are saved, and the probability of success increases. Because with an equation, we can predict a new biological activity, and we can create. Because if you create a molecule, you know what the X sub I are, those who introduce the equation and deliver it to the predicted P and C50, then that an example of this century, 2012. Published in this journal, The Medicinal Chemistry by researchers from the Pfizer laboratory, that is Pfizer Pharmacy. I told them they were the first to put their eye on this when they said it can be predicted. And then we are going to save millions. If we can predict, and here there is an analysis published by themselves where they used free Wilson equations. Then you say, this was from the 60s. If it is still used, look, mathematics never goes out of style. What is being updated are the type of molecules. That one can study and predict, but the background mathematics will always be the same. Then it says, maximization of lipophilic efficiency, use of the analysis of free Wilson in the design of acetyl cocarboxylase inhibitors is a type of strategy to create anti-diabetic molecule. And who did it? The following to great strides. Here it is. And we are going to do this type of analysis. We have two families proposed by them. A family with an aromatic ring of 6 atoms. In particular, with a substitute here in the carbon group, we can have different heteroatoms in the aromatic part X. It can be carbon or nitrogen and different Y, or we can have smaller rings. What is the name of Pirasol? We have a pirasol already fixed of 5, but we can have 2 substitutes, one X and one Y, and we can have another R substitute here. Then how to know which are the best combinations? If the ring of 6 or 5 is convenient, if some particular R is convenient, a strategy would be to synthesize the large molecules possible. But we will never be able to synthesize them all. How many they synthesize? 948 analogs, a brutal amount. I believe that there are easily about 20 doctoral theses in that amount of compounds or more. The thing is that 948 molecules is something unassailable for a normal academic laboratory. Already, within what is a doctoral thesis, I have known that the maximum have been around 100 to 120 molecules as an exceptional case. In this time, sometimes some people have boarded the 50 molecules. We have here analysis of free Wilson, who finds an equation that correlates activity versus fragments. And look how interesting with this information, this new derivative is posed then. The best group is found a group terbutyl, and the best R is found in this case an Indra. So then, how is that molecule 28 proposed? And ask me before the equation. If it creates a new molecule, we can create a new molecule from the numerical equation, so it generates visible information. We go to the first case then. We already have this study that is a study of free Wilson. Then, the first thing I'm going to teach you is how a study of free Wilson is done. It says anti-adrenergic activities of bromophenylethylamines in dimethyl disubstituted in meta and para. Ask what is an anti-adrenergic. Perfect in this particular case. OK is an antagonist of beta-adrenergic receptors. Very well, it is a beta-adrenergic antagonist. These molecules were studied by their potential as antihypertensives. That is, one of the potential applications. It is similar to adrenaline, the studied pharmacophore. Very well. That would have the adrenaline. Instead of a joke, very well, alcohol, and here, hydroxyls, very well the catechol system, and this, if it were adrenaline, and if it were noradrenaline with 2 protons instead of the 2 measures, and then those transformations make this happen to be now an antagonist and not an agonist, and this is like chloride salt. This ActL means that this is protonated, and it is a chloride. Could synthesize all the possible molecules difficult we have to vary in X and Y different fragments. They wanted to study a series. The antagonist activity is preserved when this part of here, the ring with these fragments, then to create new molecules we try different X and different Y. As we do not have unlimited resources, we are going to synthesize a narrow amount that is expressed here. Then first in the table, we have the following. I am going to divide the table by the center, because this table is divided in the center. Is the same table that is repeated there, and towards there, that should be down, but by space it is to the side then. I have that there is a goal, and that there is a stop, and the biological activity that is log of R, one part by itself. This is an ancient way of expressing log 1 divided by C is the log of 1 divided by EC50, that is. It is 1 divided by that minus log of IC50. This is the PC50. That is what is expressed there as log 1 divided by C746, 816, etc. So down in there we have that the compound 1 only has hydrogen, the compound 2 has hydrogen and fluoride. How many molecules are in total? And they are 11. And therefore here to the other side, perfect, they are 22 compounds. I already know that they understood this. Look at the fragments. They are hydrogen. That is, hydrogen is not to have anything. There are no fragments, in other words, chlorine, bromine, iodine, methyl. Ask which of all these 22 is the most powerful as an antagonist. The one that has the greatest efficacy. The least IC50 or the greatest. What happens is the least IC50, that is, the greatest IC50I with that, and therefore the most powerful is. If we start here to look for, I cannot find it where it is on the right, where joke and the last one, and then the greatest power. Is this, remember, that greater IC50 implies less AC 9.52. IC 59.52. Then the question that I am going to ask you, which is the IC50, mathematically speaking? Then the IC, and it is 9.52, and that is the most powerful. Then the question is, which is the IC50? The question is, what is the IC50? And the question is, the IC50, they had a dimensionless scale. Dimensional scale, and then 10 raised to less not true to less 9.52 thanks. And if we apply the calculator quickly to get to the real value, let's see how much it gives us. To me, it gives me 3.02 by 10 to the minus 10 and 3.02 by 3.02 by 10 raised to minus 10. And there we would be reaching the value now expressed in this way. That would be the IC50. Then this is the IC50, the IC50. And now we are going to say molar. The IC50 molar is 3.02 by 10 raised to minus 10 molar. Then we take this now to nanomolar scale. Then the IC50 EC50 would be the following. Remember that nanomolar is equal to 10 raised to nano minus 9. Not true. And then it would be 0.302 nanomolar, or I am wrong. And because it is to run the comma once, so that we have the minus 9 not true, I would stay 0.3 by 10 raised to minus 9. And that is nano 0.3 nanomolar. That is, the power is very high. 0.3 nanomolar is something super powerful, something as an antagonist very good. So very well, 0.3 nanomolar is something that hopefully we could get, because it will be quite selective, and you could calculate everything. But here, the analysis that was done reverse. That is, if the researchers published this column, they started from the IC50 and the IC50, transformed it into a dimensional IC50, so the transformation does not get confused. It be well done. Be careful that QSAR has a problem, and unlike the docking studies, when QSAR, you leave a wrong molecule, either in a value, in a fragment, in a property, everything comes down. Drax error to the end. A molecule that is badly done, badly reported, does not completely ruin the study, so be very careful with that. You have to always review things many times, and then note this. We are saying that 9.52 is the best. That is, according to this table, the best. Substitution is a metabromo and a paramedic. But the question is, will that be the best possible combination? And if it was the researchers, all the possible combinations of fluorochlorobromo, iodomethyl, and dimethylhydrogen in meta and para, the answer is no, because if they had done all, and there are only 22, then they did not do all the possible combinations because it is very expensive. Let's make an equation that predicts which ones are going to be the same fragments the best possible. That is, note the approach. Frey-Wilson has an approach of this, is called interpolative. Then the approach of Frey-Wilson. Frey-Wilson is always an interpolative study. Allows you to predict. Using the same fragments that are part of the study, you cannot create a turbutillus. Then, if the question is, teacher, will it be good at turbutillus? We cannot. No, with Frey-Wilson, because turbutillus is not part of the fragments that you are studying. It has to be with the fragments that you are studying. You will be able to predict well. And what you have to do next, you have to make a Frey-Wilson matrix, which is a table where we have, look here, is a table that we are going to do in Excel, in statistics, or a software where you are going to put compound 1 up to n up to 22. Then to remember more or less what it was here, you can place the variations of fragments, you can place the smile code, or whatever this is to remember more or less what each compound was. It is not report again what is in meta and what is in par. And we have the observed biological activity. So what is there again is the PIC50. This is very important, is the PIC50 experimental. Always, biological activity has to be an experimental value, what is on the right. With this, that did not have it in the researchers at the beginning of the study that came later. That is the PIC50 calculated, okay, or predictive. That came from the Frilson equation. From the Frilson equation, the activities for the act molecules that were part of the model, but that column was not before, and we have the following. Let's go here. The compound 1 had hydrogen in meta and hydrogen in para. Therefore, what are they for? Variables x. First, the biological activity is the variable y. The biological activity is our unity of the equation. Exactly those are the x sub I of the compounds. Exactly then, y corresponds to the dependent or independent dependent variable. And we then have a variable that we're going to call here x sub 1. Then we have another variable x sub 2, x sub 3, etc. And until the end, how many would be here? 3, 4, 5, 6, 7, 8, 9, 10. The last x sub 10. Then we have 10 variables, and the variables are presence or absence of fragments. When the EQ fragment is absent, we are going to say that its contribution is 0. There is no certain is absent. And when the fragment is like the molecule 2 that has fluorine para, we put a 1 there, and therefore there is nothing else in para. It is filled with zeros. There's nothing else in meta either. That is, when I say nothing, I mean that the rest are hydrogen, and therefore there we are controlling a matrix with numbers where we have zeros and ones. Let's see another one. For example, this one here, what happens with this one? Because there are 2 there, because it has. Very well. A methyl in meta and a fluorine. For that, there are 2 ones, but all the rest are going to be zeros. There is no iodine, there is no bromine, there is no chlorine, there is no fluorine, there is no fluorine in meta. The same bromine, iodine, methyl. So there we would have the rows of each one, in particular then, for reasons of visual simplicity. The zeros are not put, but I think they are capturing the idea. Then we have that we are going to do multilinear regression now with a y and with several x sub. We can do multilinear regression then now. What regression methods we have? We can do classic multilinear regression. Yes. And that I am going to explain when I demonstrate the Hans equation, because the Hans proposal, the behavior is better explained in logarithmic terms. I mean, the biological behavior of a molecule. The biological behavior of a molecule is explained better, and that comes from how the molecule goes through biological membranes. And I am going to explain it now. This way of expressing the model so far, it has worked well. Then empirical part, that makes a hypothesis, a proposal with empirical data, and so far worked well, but it is also reported in literature what is called non-parabolic models of lipophilia, already with equations with other exponents. Between the log and one part of the observed versus the calculated. Now some have as errors, and in logarithmic terms, I was saying that this error could be more considerable, of course, if on a normal scale there is no care, if there is already a good observation there. Let's see first with the subject of closing this idea to be able to look for correlation. You can apply classic multilinear regression, and you can also apply some other different method, such as partial minimum squared analysis is another type of more complex statistical regression. Partial minimum squared analysis. If they have access to that statistic and they want to use it, is abbreviated as PLS. Serves when the database is extremely large and when the number of descriptors exceeds by much the number of biological activities, so be careful with that it is no longer something that says I am going to occupy it like this. Immediately, the PLS is occupied, I repeat, when they are databases of thousands of molecules with thousands of descriptors. And there, the number of descriptors exceeds, numerically speaking, by much to the number of biological activity varies. Do a statistical analysis of partial minimum squares. But in most of the cases, a classic multilinear regression is enough in answering the question of the error, because there's little time left but to close this main idea here of the table formulated. Remember that this column was made at the end with the equation obtained, say, biological activity value was predicted, and as Christian says, we have that value. It is impossible. In some cases, it gave very close, for example, this 1816, of course, and one says the other, and the decimals will be the same. There is probably a difference in the third decimal, but it is already very similar. Not true. Then there are differences if they are similar. There are some very close and others that move away a little more. But how much is the tolerance to that? It turns out that a good prediction is the one that has a delta P and C50, experimental minus P and C50 predicted minus there. I am missing space. I go down -3 times the standard deviation of the proposed model. P and C50 predicted minus P and C50, experimental, minus the P and C50, -3 times the standard deviation, has been expressed in some texts a little older that it would also be enough to say that it is smaller to a logarithmic unit. Example. Suppose this value of 7.5 already 7.5, not true. What happens if the prediction had been 8.6? I would be going from a logarithmic unit. Not true then. The prediction is bad. If the prediction were 8.5, they would be at the limit now that almost always that this criterion down here that always coincides with this stricter criterion, this one up is the stricter criterion, -3 times the standard deviation, and that in general multiplication is rarely superior to 1, mathematically speaking. Then let me close the idea, and when you look for the regression equation, they get to this. There is the equation, the Fries-Wilson equation, where we have up here that is, That is that easy. And C50P and C50 equal to minus 0.3 by fluorine meta. That is to say that it was fluorine meta the variable x1 plus 0.2 by chlorine meta. That was the variable x2 is the standard deviation between the middle of each term until the last value, that is this here. I put it in para, that the variable x10. And we finally have the intercept 7.82. The intercept of the equation recalls that this is a multilinear regression equation, asks based on this equation quite long what is the worst substitute and in what position. Now comes the interesting part of it. Exactly what is the most negative? Very well. The first is the only negative then. If you are there working to design a new drug, are you going to put fluorine meta? No, because I have 0.3 left to this value here. Then it does not contain which is the best substitute. And I am going to look for it, where it will be. That, and then it is convenient to have yodo in para, if which is the best in meta. 1 point. This is for I cannot have two substitutes for the problem. But no, but this is for very well. This is for 0 points, thanks. That is fluorine 0. Iodo in meta. Therefore, logical conclusion, exact. We have to create this molecule. That the authors do not have it reported in the table because they were not able to synthesize the possible existing combinations iodo in meta and iodo in para did not exist in their table. Because look, no, because these compounds were very toxic. They had another effect. We are talking about that. This is from the 60s. And then look here. But if there is a pharmacy of literature that has been designed by QSAR, and as for example, norfloxacin, quinolone, and look if you come here with iodo, for example. Look at this here. Look with there. Iodo, it was not the diodo, it is. With iodo, in para with iodo in meta. And it was not with both, therefore. They are creating a new molecule. And now the final question. And what biological activity has this new molecule already? But numerically speaking, what value of activity it has? Then the PC50 would be the same. Exact. It would be 0.579 for iodo in meta. But when iodo is in meta, that is equivalent to 1. Remember that here it is 1 and zeros. 1 exists, 0 plus 1.429 for iodo in para. That is for 1 and what else perfect plus 7.82. 1 the intercept. And I am going to the shot here to the calculator to predict the value quickly. Of course it gives me 9.8, 9.821. But as that value is higher than what was in the table. And because the table is the highest value of 9.5, approximately then, we have that we are proposing something that has a value higher than the study group. Therefore, the probability of success is high. That is the background strategy. That is to make a QSAR study at high rates. This is the simplest QSAR study that can be done, that is called free Wilson analysis. Be able to execute it satisfactorily. If you need to have a good data dispersion, work hard with the statistics, because it will not necessarily immediately obtain statistics, and there come the adjustments to the